So the title of my talk is Lattice Theory and Algebraic Models for Deep Learning based on mathematical morphology. And I will give you a complementary perspective from what you see in the morning by Petros Maragos. We have some common background in the mathematics we will be using. But in my case, it will be more from a representation theory point of view. So let me start by a joke. Probably most of you working on this field, you should do it because you need to survive, not only because it's an interesting field of research. And probably we need to change it a little bit. And nowadays it will be like work on transformers or perish. So let me be a bit more serious. What is the goal of this talk and in general of this line of research? Is trying to understand a little bit better what happened with deep learning and these very complex deep learning neural networks, which combines different mathematical operations. And due to this optimization process, you can really learn classification and prediction in a very sophisticated and impressive way. So there are many different perspectives and paradigms to address this mathematical modeling of deep learning. And I am just giving you 4 recent examples of very different branches of mathematics where you can find a connection between what is done in deep learning and what will be a more fundamental perspective on that. So it can be things related more to numerical analysis, like these Kolmogorov-Arnold networks, where instead of using convolution in a very standard way, you will use splines and you will have something more compact from a numerical viewpoint. You can have people interested on category theory, trying to have very abstract, the most abstract perspective from what it can be done in this field with the different architectures and how you will move from function to functors, the element we were discussing in the previous question, which is usually the highest abstraction you can have, but it's not always the most useful from a practical viewpoint of understanding what is really happening on these systems. And then you have the perspective, one of the most probably successful ones from my viewpoint is the one relating tropical geometry and all the nonlinear aspect of neural networks and deep learning, which was the topic of Petros Maragos. And I just include another recent paper by other authors. And then for people working on the equivariance to group on transforms perspective, how to get systems which are equivariant to transformation of your data, typically on images, probably the most successful approach to model mathematically that aspect will be the ones using PDEs, and how you can introduce symmetries on the system using PDEs and the corresponding way to implement this in neural networks. So here I will try to give you some ideas of how mathematical morphology can be useful to represent in a very general way, a kind of universal representation of what is happening in a deep neural network using mathematical morphology. So, and I will just discuss a very simplified representation of what happens in a typical layer of CNN. Probably most of you are very familiar with that. So you have a kind of composition or combination of things which are linear. All the things we were discussing, Marcos was discussing a lot in the second part of his talk, which traditionally in the neural network will be the convolution, or in the case of the fully connected, this will be just the product between the matrix and the vector. So all that is linear mathematics somehow. And then you have, because it's just how the perceptron is formalized. You have a product, a dot product between the weight and the input, and then you have the activation function, which is something non-linear. And this is the success of this system, is including the non-linearity. And then you will compose all these things, and by composing layers, you will be able to learn very complex geometrics, which can be understood by the tropical geometry perspective. So basically, my point is you are combining a very different kind of mathematics, something which is linear, which is well understood, with other kind of activation functions, which are not always easy functions to model. So when you want to have something which is from a mathematical perspective, a complete model of what is happening there, it's not always easy to find what is the correct approach to deal with that. So there are a lot of people working on universal representation of what is happening on the linear part of the networks. And then you will have very simplified non-linearities, which will be somehow transparent to this universal representation of the linear part, especially on convolution. And here I will try to consider globally what is happening in this black box, like a non-linear operator, psi. And my goal basically will be how we can represent in a universal way this kind of non-linear map, psi, which usually will include a kind of local process given by the convolution in the case of the CNNs. Okay, and this is where a mathematical morphology will be useful for that, because we have an universal representation theory of nonlinear operators using these morphological operators. Okay, so this is basically the motivation of my work. So I will probably skip some of the elements because we are already very late today and it has been a very long day. So I will probably stop after the point 5 of my talk. So let me start by another reminder of mathematical morphology. This is the third of the day, and I think I can be a bit complementary to the one we were discussing. Because my point now will be just to say, probably you are, even you, is the first time today you hear about this mathematical morphology thing. There are many aspects of mathematical morphology which are probably familiar with you. Familiar to you, sorry. So the element I will be using myself here will be this abstract algebraic formulation of the theory. Okay, so I will discuss that in a moment. But there is other branches of applied mathematics where mathematical morphology plays an important role. For instance, one of the very interesting from my viewpoint is the relationship with the random set theory and the notion of Choquet capacity, which allows you to characterize any random set similar to the way you characterize a random variable. And for that, you will use mathematical morphology. There are also very strong connections with something Petros was mentioning in the morning, idempotent mathematics, all the works done by Maslov, and the tropical geometry we were discussing. The continuous formulation of mathematical morphology are just particular cases of the first order Hamilton-Jacobi PDEs. So the viscosity solution of these kind of PDEs are also morphological operators. So and this one is related to convex analysis. So basically, my point is what I will be using today are tools which probably you have been using in other branches of mathematics before that. Okay, so let me consider probably the most important point of my talk, which will be this universal representation theory for nonlinear operators, which is something classics, very classical in mathematical morphology. So we have been discussing during the day a few times on this idea of complete lattices and what we call operator between two lattices. And this is what we call a lattice operator, psi, here, phi, which in order to, for the sake of simplicity, most of the result I will show you will concern something we call an increasing operator. So it's an operator with respect to the partial order of the lattice. So remember, a complete lattice is a set with a partial order such that we can define an infimum and supremum for any subset of this lattice. Okay, so we have a partial order connected to this set. And as I said, the simplest way to deal with this representation theory is to focus on increasing operators. I will show you later what is the more general equation, but just let's focus on that. So operators which are isotone with respect to the partial order. And the two basic operators in morphology are the dilation and the erosion, which are the operator which distribute with the dilation with the supremum and the erosion with the infimum on this lattice. Okay, so this is a very abstract formulation of dilation and erosion. And then the canonic example of that will be of dilation in the case of when you are dealing with set is the Minkowski sum of two sets. This is an example of dilation, or this kind of dual sum, which is something we call the erosion. Okay, so just, for instance, the dilation will be just, you take one of the set, and you translate the second set to every point of the first set, and you take the union of that. This is the Minkowski sum of two sets. And the erosion is something which is dual to that, kind of subtraction of two sets. And this is the typical operators we use in mathematical morphology when you are dealing with sets. And then we can generalize that to functions, and we have something which is just the supremal convolution and the infimal convolution. Okay, but these are just examples of this more abstract dilation and erosion in the case of a complete lattice. And so in the case of an increasing operator psi, this is the more general form of this representation theorem I was mentioning. So given a complete lattice, any increasing operator on this lattice, which preserves the greatest element of the lattice, can be represented as the supremum of a non-empty set of erosions. Okay? So that means for any nonlinear increasing operator on this complete lattice, you have a family of erosion, remember, are the operators which distribute with respect to the infimum, which will give you a representation of this operator. So this is a very powerful general result. You have the dual one with the infimum of dilations, but obviously here you don't know anything about the erosions, how they looks in this very general setting. Okay, so we will now try to be a bit more concrete. We will focus on more practical result, but it will be just examples of this general theorem. Okay, so that was something which was proved in the late 80s, 90s, but the original theorem on this representation theory is something which originates at the, let's say, at the beginning of mathematical morphology, which is a result by George Matron, which in that case we focus on set and the power of set as the lattice where we're working. So the partial order will be just the order between the set, the inclusion order. And then you can prove any increasing set operator can be represented as the union of a family of erosions. Erosion, remember, is the dual of the Minkowski sum, or an intersection of the Minkowski sums, the dilations. And the erosions will be element, sorry, of the kernel of this operator. And so this is already very useful because that means any translation equivariant increasing set operator can be rewriting as a union of erosions. So in general, you don't know what is the corresponding family of sets A, which are part of the kernel, but you know that exists. But that can be infinity. And the other aspect which is important in this representation theory is the fact this kernel is very redundant, because you are taking the union of these erosions, many of these erosions will not play any role in the representation. So somehow it's not a minimal representation. And there is a significant contribution by Petrus Maragos, a very old one, let's say, which is more a minimal representation in that case. So we will find something which is a kind of basis of the operator. So that operator will be now represented by a set of sets M, will be part of the kernel, but you will add an additional condition to avoid the redundancy of the representation. Okay? So this is just, the previous result is just for increasing operators. So in the general case, when you have a nonlinear operator, which is translation equivariant, I mean, the point here is we're dealing with operators which are acting on the space, typically for processing images or for dealing with sets. So this is where translation equivariance appears like one of the main fundamental assumptions of what we are doing, like convolution, for instance. But when you want to be more general than the isoton property of the nonlinear operator, you can have a more general representation, and this time you will combine in the universal representation something we call an erosion and an anti-dilation. So it's just a bit more complicated from a mathematical perspective. So this is why I will focus on the increasing operators, which are just like half of this universal representation. But keep in mind, we can have something more general. But the basic ingredient of this representation theory are just very simple bricks, which are these either dilation or erosions. So this is why I call this theory Matterhorn, Maragos, Bannon, Barrera representation theory, because of this series of theorems generalizing that. Okay, and now you can, that was for set, for the power of the Euclidean space or the discrete space when you are working on set. But you can also have an equivalent representation theory for the case of functions. And then you will replace the Minkowski sum for this kind of infimal correlation or supremal convolution. And then you will have a supremum. You will take a set of erosions now for functions, and you will any nonlinear translation equivariant increasing operator can be represented by this supremum of erosions. Okay, but notice here we have the parameters which appears, which are these functions ji. So in general, we don't know what are these functions. But now, because of deep learning and because of this possibility to learn many things, that means that can be one of the parameters we can learn on this representation theory. So that means basically any nonlinear increasing, let's say we're focusing on isoton behavior, any nonlinear increasing layer can be in fact represented by using these bricks, these erosions, these supremum of erosions. Okay? So let me give you an example of what can we do with this universal representation theory. And we will focus on, in the block I was showing you before, one of the elements of the nonlinear part of these networks were the activations. So let's revisit now the activation from this perspective of mathematical morphology. Okay, and we try to see if we can do something more general or understand at least what we are doing. Okay, so I mean, probably all of you in this room are familiar with this activation function or this kind of nonlinearities which appears. For instance, something which is very common, one of the most useful activation functions in deep learning is this rectifier linear unit, ReLU, which is just taking the positive part of the output of the neuron. So that I don't know if you notice, I am using this delta, which is the typical notation I will use for a dilation. So I will just show you, this is just from an algebraic viewpoint, this is a dilation because this is an operator which distributes with respect to the supremum. But this is true with all the variant you want connected to the ReLU, leaky ReLU, parametric ReLUs, I mean, all these things. When you include the bias, the scalar, which can play a role also in the activation function, this is something also which will be still compatible with this perspective of having a dilation. The max pooling layer, for instance, is a typical example also of morphological operators. Again, it's a dilation. You are just combining, taking a maximum in a local neighborhood and then downsampling. So that will satisfy also the properties of being a dilation. Also, this is the max plus layers Petros were mentioning, the max out. All that are operators satisfying algebraically the properties of being increasing, commuting with the supremum, and therefore being dilations. Okay? So that means the nonlinearity, most of the nonlinearities which appear there are dilations. But that means also we are combining different dilations. For instance, the activation function is a dilation. If you are using a max pooling layer, it's also a dilation. So you are composing operators which from an algebraic viewpoint are share a lot of properties. Okay? So we can have something more general than the two, the most general form we can have for the ReLU or the pooling using just this universal representation theory I was showing you before. So instead of having just a dilation, which is the ReLU, for instance, we will take an infimum of the dilations. So we can take a set of these functions here, this set of activation, which are just parametric ReLUs, the more general form you can have of the parametric ReLU, and you take the minimum of them. And you know, we can prove just as a particular example of the universal representation theory, any nonlinear increase in activation function can be represented by this form because of the theory we have discussed before. And for the pooling, we can have something similar. Any increasing pooling operator can be represented as a minimum of max pooling operators, where you will learn also the weighting you are using for the pooling operator at each one of the elements. So these two formulations are just considering what is done currently and considering that as the basic ingredient for this universal representation theory. So both are just examples of the result I showed you before. With the example I was, I mean, when you check these, the mathematics of this activation function, they are just the examples Petros was using this morning from a different perspective, the tropical polynomial interpretation of that. Here is more from a operator representation perspective, what we are doing. Okay? So that means in the case of a convolutional neural network, all the nonlinear part, you have on the one hand the convolution, and you have all the nonlinear part, including activation, pooling, all this ingredient. You can write that as just a nonlinear operator, which will be represented by a minimum of a set of dilations. And this dilation will be something integrating both activation and pooling. So all the parameters which appears either on the activation or on the pooling can be learned. And you know, this is the more general activation function you can have. I mean, the more general nonlinear part of the network you can have using this representation theory. Okay? So let show you an example of we can use that in a very simple way. So in this example, we will consider that it's a very simple convolutional neural network. And basically, we will use two layers. And this is the, here you were just visualizing. So this is MNIST, you're familiar with that. It's a 10 class classification problem. And basically, you need to separate the different classes, the 10 classes, which are just digits. Okay, and this is one of the toy examples we use to prove if a neural network is learning and what is happening with that. So in this example, in fact, we're considering two layers, and we fix the convolution for the moment, and we will just learn all the nonlinear part of the network. The activation function, where I showed you before, which is more general than the ReLU, is a family of ReLUs, taking just the minimum of them, integrating also some pooling. Okay? And the interesting part of this result is we initialize the network, and the convolution is totally random. The weight on the linear part are totally random. And we will learn only the activation functions, only the nonlinear part. And just learning the nonlinear part, you get the result 92%. And all the linear part is totally random in this problem. And this is the kind of activation function you are learning. Remember, you have like a bunch of ReLUs, and you are basically something Petros was showing this morning. You are getting something which is a tropical polynomial of high order, and then you are taking minimum of these polynomials. So this is the nonlinear part of the network is basically that. And just with that, you get 92% of accuracy. And then when you learn everything, the linear and the nonlinear part, you get 98%. Obviously, you get better, but this is just to prove learning the nonlinear part of the network is very interesting, at least in relatively simple problems. So here you are learning just this part of the network, which usually is not learned at all in the classical paradigm. The only thing you are learning is the linear part. Okay? So we have a more table of results with that. I will skip this part. And another aspect which is interesting nowadays in this field of mathematical modeling and understanding of convolutional neural networks is the idea of equivariance to the group of transforms of your network. So the idea is to go beyond the translation equivariant of the convolution. And for those of you who are not familiar with this idea is, let's say you have the image of a flower, and you will take a rotation of the flower, and you will like your network recognize it is still the same kind of flower up to this rotation. So somehow you need to introduce in your network the group of symmetry of the rotations. Okay, so there are different ways to do that in the field. One of them is something called data augmentation. You are probably familiar with that. You take your flower to train your network, and you will train the network also with all possible rotations of the flower. And you will say to the network, well, this flower and the rotation of 10 degrees and 20 degrees is just the same flower. So this is a very empirical way to impose this symmetry to rotations, for instance, in the network. And the other one is to use group intrinsically group transforms in your network. And typically that will appear in the convolution. So instead of having convolution on the Euclidean space, you will have a group convolution, which will play the important role in order to have this equivariance and symmetry in the network. Okay? So the point here in this result, I will go fast with that, it was just to use group morphology to have a universal representation, which will be also equivariant. So remember in the previous, in the most classical theory, everything was working fine for the case of the translation equivariant operators, because we were using supremal convolution and the dual operator, which are translation equivariant. Okay, so if you want to have something more general, you need to replace this supremal convolution to something which will be a equivariant in the sense of the group of symmetries you are considering. So this is the part of that. And the idea is just to generalize when you have, and that works well in the case of a group acting on an homogeneous space, which is I mean, this is from a theoretical viewpoint, what we need for most of the applications, so that is not a problem. And the idea is to generalize the Minkowski sum for Sept to a Minkowski group transform. Okay, and now basically we will have operators acting, instead of acting on the power set of the set, will be acting on the part of the group. So we will have subset of the group, and we will be considering the universal representation of this operator psi now acting on the part of the group instead of on set as before. And the first ingredient we will need is just, as I told you, the equivalent of the Minkowski sum between two subsets of the group. And there is a classic theory on group morphology, which provide us by Roerdink and Maragos, which provide us this dilation and erosion for groups. And this is what basically we will be using. And then, like in the case of the group convolution, we will be needing, because our initial space, typically for images, is something on the Euclidean space or the discrete space. We are not working directly on the group. We need something we call the lifting to the group. We will go to the space to the group. We will be applying these group operators, and then we need to have a projection operator to go back to the space. So this is something which is relatively classic in group morphology. And for the case of what we call Boolean morphology for groups, subset of element of the group. And I basically, as we will start here with, for instance, this is the commuting diagram typical for this kind of group operators acting on initially on the space E, that can be the Euclidean space or the discrete space in the case of images. Then you have the lifting. You will have your operator on this part of the groups. You have the projection, and you will have an operator which is equivariant on the homogeneous space, preserving the symmetries of the group. Okay. So this is for the case of set which are equivariant. I mean, or operators psi acting on set, integrating this equivariance assumption. In the case of functions, which is done in the neural networks, typically we need something which is the equivariant of the group convolution for the mathematical viewpoint. So probably most of you are familiar with this idea of group convolution. So basically, we replace the translation of the kernel by the product of the two elements of the group. We're integrating now on the group, and usually here you have just the translation in the case of the standard convolution, and here you have just the product with the inverse of the element which is acting on the element of the group. So this is a typical example of this group convolution in the case of the SA2 group. So this is something which is used in convolutional neural networks which are equivariant. Typically, this is the kind of convolution you will be using. And for the case of morphology, I will just introduce the similar group supremal convolution and infimal correlation. So these two operators are just the transposition by changing the algebra. Remember this way where we move from the sum and the product to the supremum, the max, and the sum. So this is a very simple way to rewrite in the group convolution in this max plus algebra. And this is the dual operator. And we can have something more general than which will combine an algebra which is a max plus and a max times algebra. And these are equivariant operators on this, the equivalent of the convolution of this on these more nonlinear algebras. And when you have this basic dilation and erosion for groups, we can now try to formulate the equivalent of the universal representation theory for any equivariant operator. So basically, we need to define the kernel of the operator as it was done before and the minimal basis, which is just the counterpart of what we had before for the Euclidean space, in this case of the group. And then we can just prove we can have any equivariant psi operator acting on the homogeneous, on the group by just the supremum of these group erosions. And this is on the group, and using the lifting and the projection, we can have this group universal representation result using just the lifting and the projection on the homogeneous space initially. Okay, so the take-home message of this result, of this general result, is all the if you want to have nonlinear functions on your network which are equivariant, you can just use this universal representation. So you will, instead of using just standard activations or standard translation equivariant pooling or similar operators, you need to replace them by these morphological group operators. And then you will have all the nonlinear part of the network will be equivariant. So, so that provides you all you need in order to have the more general nonlinear part, which satisfies the equivariant properties on your network, and which will not be able to be represented by the group convolution, which is used in the linear part of the equivariant networks. Okay? And for the last part of my talk, I will, because what I was discussing until now, it was basically focusing on the nonlinear part of the network. Remember, I saw you have the convolution, or you have this linear product between the matrix and the vector in the network, and then you have the activation on the red, which is the nonlinear part. So if you were really to understand what is happening in a neural network from a mathematical morphology perspective, we can try to see also if we can do something with the convolution. Do we have a mathematical morphology perspective of the convolution? And then we will have something which is more compact, in the sense of we will have a universal representation from a mathematical morphology perspective of everything happening in the network. Okay? So this is what I will try to show you now with this perspective of the convolution as an operator on an inf semi-lattice. And basically what I will do is will be to change the perspective of convolution, and we will work on the frequency domain. And we will try to introduce a partial order on this domain such that we can have a lattice, or in that case, it's going to be something which is half of the lattice, an inf semi-lattice, and then we will be able to have a representation of convolution, which will be an erosion from an algebraic viewpoint. Okay? So let me be a bit more precise about that. But this is basically the goal of that. And my inspiration is something done in the 2000. It's a very unknown kind of work where signal processing, the standard filters and many things done in traditional signal processing will be considered from this algebraic perspective. And the idea will be, as from the very beginning of my talk, I was mentioning the idea of a partial order, we need to have something where, in order to have a lattice representation, we need to have between the operators a notion of order between the element and then between the operators themselves. Okay, so in order to have a lattice representation or a semi-lattice representation of the convolution, we need an order which appears in the convolution. So the idea of this work by Renato Keschet was the following: is the idea of when you are processing images using convolution, you can introduce an idea of simplicity. You are getting something which is simple than the previous one. So the simplicity is like a partial order. Obviously, you need to be more precise about that. But the intuition will be, let's introduce a way to measure how much sample is a signal with respect to the previous one. And that will provide you a partial order. Okay? And then there are different alternatives in the way you can introduce this idea of something more simple, something providing you this partial order between the different transforms. Okay? But something to notice already is something which is not symmetric, in the sense of you are able to get sample and sample. You are simplifying, but you cannot get something more complex. So basically, you are only able to go one way in this partial order. So that means we will have something which is not a complete lattice. We will not be able to define simultaneously something which is the infimum in terms of the simplicity and the supremum in terms of the simplicity. Okay? So this is a limit in the sense of we cannot have both erosions and dilations in this approach of the simplicity I was just discussing here. Okay? So this is basically the philosophy of this approach. And now, because we will focus on something which is interesting from convolution, it will be the modulus of the transform. It will be the energy of the signal. So we will work on the Fourier domain, and then that will help us to introduce an infimum between two signals according to this partial order. Okay, and we will be able to give an interpretation of convolution just as an erosion. Remember, the erosion will be something which distributes with respect to the infimum. So we need to define an infimum such that convolution will be something which distributes with respect to that. And so, I was saying, we will consider the convolution is just an erosion. And the way we will do that is let's consider the representation of the convolution using the convolution theorem. So basically, we're working on the Fourier transform. And we will have the following spectral partial order. So two signals are order. So F is smaller or equal than G in this spectral order. If in the Fourier domain, if you take the modulus, you have an order for every frequency, and the phase are equal. Okay, so we have here a partial order between the two signals. So this is just a partial order. It's not a total order. That means two signals are not generally ordered between them. But using this partial order, you can prove the erosion, the convolution, sorry, is an erosion because it will distribute with respect to this partial order. Okay? And we have a complete semi-lattice because we can define the infimum for two signals. And this is what we will be distributing. Okay? So basically, the idea of this representation is to see convolution as an erosion on the corresponding lattice, semi-lattice, sorry, we use this partial order on the Fourier domain. And we have an adjoint dilation. to this erosion. So the fact we cannot define a supremum doesn't mean we cannot find an adjoint operator using the Galois connection we were discussing before. So we have also a dilation, which is just using, is a convolution in the Fourier domain using as kernel the inverse of the kernel we were using. And this is a dilation in the sense of it is the smallest element which is bigger than the erosion. And then you can have also an opening, which is the composition of the erosion and dilation, which is in terms of the filtering, the traditional signal processing perspective is just the ideal linear filter. Remember, an ideal linear filter is a filter which will either preserve the value of the Fourier transform at a given frequency, or it will be put to zero. This is what it is. So it's an idempotent operator, as usual in the case of the openings. So what is the interest of working now from this perspective of seeing convolution like an erosion? So now you can say, because we know any operator can be represented by a supremum of erosions, you can consider a supremum in the sense of what is happening on the frequency domain, and consider that as the way to generalize a family of convolutions acting on the image from this algebraic perspective. Okay, and I will give you an example of where we can apply that straightforward. I don't know if you are familiar with the scattering transform. The scattering transform is a multi-scale representation which is used by Stefan Mala and co-workers as a mathematical proxy of what is happening in a neural network. And they basically will decompose all the information of the signals in the frequency domain, and you will use a localization of the information of the energy for each one of these part of the spectrum. And then you can do that in a hierarchical way, and then you can learn how to combine these contributions of that. So basically, what we're doing when you have this representation with disjoint part of the spectrum, you are basically using our universal representation theorem, because any of these filters, I don't know if you're familiar with scattering transform, but basically the phase is put to zero. So if you remember in my partial order, the phase should be equal in order to be able to compute this supremum and infimum. So it's perfectly compatible with that. And so with the scattering transform, is just an instantiation of this universal representation theory from the perspective of considering convolution as an erosion and a supremal of erosions as a combination of the different elements of the scattering transform. Okay? So, and I think I will stop here. Just a few more words about what we are doing with this representation theory. So basically what we can do now is to rewrite what is happening in a neural network just from the mathematical morphology perspective. So it will be just combining erosions and dilations and try to be a bit more general that we are doing when we decompose things in convolution, in activation function, and these kind of things. And the idea is not just to rewrite what is happening in the networks. Let me show you an example, but to have something a bit more from an algebraic viewpoint, to have something which we can understand a bit better what we are doing by composing all these operators, which sometimes can be families of erosions, sometimes can be families of dilations. So we can try to understand a bit better from this algebraic and operator perspective what we're doing. So another aspect which is important to consider also in this kind of networks, if you are familiar with that, is the idea of the hierarchical representation. I mean, in the neural networks, remember, you are basically downsampling on the space and somehow upsampling on the features. So you are a representation which is something like a pyramid, which is decreasing on the space and at the same time is increasing on the number of feature maps, and you are progressively reducing this information. So in order to have something which is from the mathematical morphology perspective compatible with this hierarchical pyramidal representation of the information, we need to have also a lattice or semi-lattice representation of the pyramid. And this is something also we can do. We can define erosions and dilations, which are just the abstraction of these pyramids, and recover things like the skeleton, and basically to see the U-net as something we, in mathematical morphology, we call an skeleton, which is something reducing the information. And so, yeah, I will skip that. But basically, it's just, the idea is to understand a bit better what we are doing now from our perspective in the networks, but also what we can replace on these networks with a more general setting. Okay, so let me go to the end, because I think the day was very long. And so the conclusion is just the idea of this interaction, or this cross-fertilization between mathematical morphology and deep learning. The motivation is just to have an algebraic theoretical understanding of all these operators we are using, and why some of them are working better than the others. We can also see how we can factorize some of them, because they are, from this perspective, they are just the same, they have the same nature, algebraic nature, so they can write in a more compact way. So we can learn less parameters, because some of them are part of the integration of these operators. We can have also more natural inverses, thanks to this idea of Galois connections. For instance, in the case of the U-net, remember you have something which is downsampling and then upsampling. In our formulation, we can see if downsampling are erosions. We can know exactly what are the dilation which should be the upsampling, in order to have something which is more, let's say, compatible with our theory. What can we say more about that? So maybe the last point, which is extremely important for people using these things in practice, and was discussed by Petros this morning, is learning these nonlinear representations using a standard optimization techniques, like the stochastic gradient descent or your favorite optimizer, doesn't work as well as in the case of convolution or sample activations. So the optimization of these more general nonlinear representations are not as easy as what we do now. So there are people, as Petros, as Marcos, working on very specific optimization techniques, this convex concave process, and other more adapted optimization techniques. But this is probably the most important part on this theory, is to have something which can be optimized as well as the standard architectures we have in the neural networks. So thank you for your attention.
Yes, thank you for the talk. So we have time for questions. Oh. Andre.
Thank you for the very interesting talk. I like very much this universal representation of the activations, as well as the whole representation of the CNN, this unified representation. So I guess from a theoretical point of view, personally, I would see there the value of representing this, as you pointed out, a very diverse collection of operations, linear convolutions, nonlinear activations, pooling, and whatever else, representing them with the same collection of operators. So this is, I think, a theoretical gain. And if one sees it from a practical point of view, one question there would be to explore, or have you explored how this universal representation of a whole neural net, meaning activations and operations, exponent convolutions and all that, how it will perform if this representation is done with a smaller basis, not the full basis, but let's say a truncated basis. This will be a practical question. I don't know whether we have explored it or it's in the future of goals.
I mean, it's one of the things. I mean, we were starting to do things, for instance, because they are, you know, very well, theoretical papers from the late 90s, trying to prove, in the case of the discrete convolution, finite convolution, we have a basis, which is the null space. I mean, it's a subset of the null space. So we have, even for the convolution, we have some ideas of how will look this truncated basis. So we were doing some preliminary work, but the point you are mentioning is, I mean, we need to go deeper on that. And let's say the fundamental drawback to be sure we're exploring this space of possible element of the basis is to have something which optimizes well. So it's optimization, which is a problem on this.
And so it's very nice, I think. I will finish with a historic remark. Jean Serra, when he heard the semi-lattice approach from Renato Sept,
you were there.
Yeah, he exclaimed, well, we have hard time convincing people to go with a complete lattice framework, and now you introduce a semi-lattice approach, so you will lose people. So it's very impressive now that after all these years, the semi-lattice approach is coming back for a very standard network like the CNN network. That's all. Thank you.
Thank you, Petrus. So happy.
Thanks for the talk. Very interesting. You mentioned at the beginning of your presentation about the idea of transformer. And well, looking more from a computer science perspective, when we talk about equivariance and all these symmetries in the convolutional neural networks, when we go to transformer, in some sense, we are kind of abandoning the idea of inductive bias because you are looking at all the data and somehow it works if you have enough amount of data, it works all the necessary relations. But this is the basic premise of transformer architecture. Do you think is there any way of reconciling transformers with the idea of equivariance and all this theory, which is, I think it's fascinating. Do you see any way of making this relation?
To be honest, no.
No.
Not at this point. I mean, it's...
Because I mean, in images, you have the vision transformers, for example, and it works fairly well. If you have the amount of data, it works fairly well. So,
but you know, they are just breaking the domain into blocks, following
and it works.
It works. I mean,
this is the impressive part.
Yeah, I mean, you should accept it works. It's impressive, the result they get. But I don't see how that things can be formalized as we were doing in traditional, because CNNs are the natural use of all the historical way of dealing with signal processing and these things. In the case of the transformers, it's more, something which someone was having this clever idea and it works, but
yeah, for sure. Anyway, many thanks.
I saw one question. Another question.
Thanks for the talk. I would say it was very interesting. I wanted to ask a question, especially because you mentioned like simplicity of representation. Plus, Professor Petros, he mentioned like sparsity for morphological neural networks. So kind of like the goal here from a representation point of view is like to find a compressed representation of our data, which aligns with like, which I mean like in ordinary neural networks, we analyze that with information theory or with compressed sensing like point of view. Do you have some intuition between like the how good like morphological neural network to compress information?
Well, other than the things Petro was showing this morning, the fact when you are using these max plus perceptrons instead of the standard ones, you have something which is more sparse intrinsically because you are not, when you are taking the maximum, it's just one of the input, which is playing a role. So basically, when you see the activation maps, as Petro was showing us, you have less element of activation, which are, so naturally you have, and then obviously the pruning is more natural because most of them are not useful. I mean, other than that, in the sense of what you are mentioning, like having a more, I guess you are asking if we can have a more algebraic representation of this sparsity formulation of the activations in the network. I don't know. Maybe something interesting to check. Yeah, but I see your point, obviously. Yeah.
So let's thank our speaker again.
So now we have the coffee break.
Coffee break with poster.
Yeah. So, and the poster will be in the same area around where we were having the coffee break.
Thank you.